I'm Vasif. I am currently working as analytics content engineer at Data Science Studio, and my interest lies in the intersection of data science and mathematics. I have been working in that intersection for a while, and today I would be giving this crash course on transfer learning. So, uh, today we would be first understanding that why do we actually need transfer learning and what is the basic idea behind transfer learning. Secondly, so transfer learning is essentially uh, transferring the knowledge from one model to another. So we would understand the idea behind transferring the knowledge, that how do we actually transfer the knowledge between the models. Secondly, we would be looking at some methods of transfer learning. There are various methods. We would explore some of them. We would be looking at some best practices that you should be working with when using transfer learning. Lastly, we would be discussing transfer learning in contrast with human growth model and human perception, because again, deep learning is a field that is based upon replicating human perception. So that's why we would compare transfer learning to humans. So why do we need transfer learning? Uh, one would say that there can be many problems with neural networks, because neural networks are not like the perfect machineries. They replicate human brain, and they could have flaws. So one of the flaws that neural network have is that supervised learning do not perform very well when there's not enough data. So transfer learning actually makes sense when we don't have enough data. And that is where the limitations of the neural network comes, and transfer learning provides a solution. So let's just visit DeepMind's AlphaGo model. I hope like some of you have heard of it. So this was a model made by DeepMind, and it defeated professional human at Go game. So it was exceptional at playing Go game. But what do you think if it played some other game, like maybe chess? Chess is also a board game. Would it perform well? Actually, no, it cannot perform well in that. And that's where the uh, basically limitation of neural network comes in. That neural networks are not able to really generalize the training, or they are not able to map the tactics learned from one game to another game. Human, on the other hand, let's suppose we had a professional Go player, and now that player is playing chess. Maybe like we cannot expect that player that he would be exceptional in chess as well. But knowing the rules, knowing the basics, well, one could say that maybe that human would challenge the other opponent, and that's what human mind can do. Secondly, uh, it's quite common that humans can learn more than one games. Like one could be good at Go, one could be good at uh, chess and other games, but neural network models cannot do that. They have a limitation that they can only master the data that they learn at the training time. So now let's talk about autonomous driving car companies. So there was a company that made autonomous driving cars, and they said that they claim that they actually minimized the risk of human lives with their autonomous cars. So and now the thing is that they trained their model for autonomous driving cars with like millions of images, and basically the model is not just trained once, but it is constantly updating to enhance the performance. and the performance is exceptional, the results are exceptional, and everything is good about this model. But do you think that now the company wants to create autonomous driving trucks, and they think that the truck drivers are not very competent over here, and they are li- life risk for humans. So they say if they make autonomous trucks, it could actually minimize the danger to human life. So with that goal, they proceed towards making autonomous truck. Do you think that they would need to train the model again? Yes, actually, they would need to train the model again. One could argue in many aspects. So, autonomous driving is basically a combination of object detection and uh, decision making, naively speaking. So, what could one say that they are basically similar in fundamental aspects, uh, like the decision making are same, the traffic would probably be the same, but there are some differences that we have to look into. One, the size of the vehicle would be very different. So the area taken on the road would be different for a car and for the truck. And based on the size, the decisions would be different. So yeah, there comes the difference. Now, secondly, the height of car is different from the height of truck. So the images taken from the car would be probably at some different and a different like alignment of different alignments, right? And if we take images from the trucks, they might be of a wider angle. They might be like from the top view. So that could also affect the result of the network. So when there's a chance that it could affect the results of the network, the human life risk comes in. And whenever there's a human life risk, the whole motive of the company fails. That they have to minimize the human life risk. So here's the thing that if they want to actually create a model uh, that uh, that could basically work with autonomous trucks, they need a lot of data. Let's suppose they use million of images for the cars model. They need the same amount of images for the truck model as well, and that could be a problem. Secondly, there is a object detection model called YOLO V5, and that model actually uses uh, 47 million trainable parameters and 392 layers. Well, that's enormous. And let's imagine that if your data is in millions, the training time would just touch the sky. Like it would take a lot of time to train the network. But here's the thing that if they don't train the model, human life is at risk. So they need a perfect training, a lot of data for the trucks, and that is a problem. Now, since we came to the problem of data, that we need a lot of data to train a new network, do you know that you are part of Google's data collection process? Uh, I think many of you have seen the image that is presented on the slide. So what basically you would have done is that you would have just selected the images that contains a road and then verified it. So this is actually a process done by Google to label the data. So once you are selecting the image and verifying it, it basically labels the data for Google that, okay, this image is of road and this is not. So this is a part of Google data collection process. And isn't it amazing that they use their audience to collect the data? But now the thing is that what is the audience size of Google? Probably most of us using internet. they have enormous audience, and data collection is comparatively very easy for them. Still, it's effort taking and time taking, but it might be easy for them. What about the others? What about the other companies? What about the other organizations? How do they collect data? It's quite hard for them. Let's suppose we talked about autonomous driving industry. Maybe they need to take million of images. They might need to spend like 5 to 6 years to collect the images, or even more. So uh, it's data collection is a very hard process, and that's why we use a term for it that is called data is expensive. And as we discussed earlier, supervised learning models do not work very well uh, when data is not enough. We recently saw that some models like VGT19 use million of images for training. Even if we talk about ImageNet, it also use million of images. So to get a better accuracy, we need a lot of data, and data is expensive. So to understand this problem, let's look at an example. Let's suppose we have a model that classifies pictures of cats and dogs in separate categories. And this model performs perfectly well. Like it gives amazing results on unseen data, and everything is fine with this model. But now here's a problem that we need this model to also predict the pictures of a parrot. Well, let's suppose this model was trained, and also we need the same type of accuracy for parrots as well, as we were getting earlier. So let's suppose we use 500,000 images for cats and 500,000 images for dogs. How many images do you think we would need for the parrot to train the model in such a way that it could provide the same type of results? Probably the same number of images, right? So that's again, we need, if we say that we need the same number of images, then we need 500,000 images of parrots. Well, that's a huge ask. So in summary, we addressed three problems. One was lack of generalization that we discussed that AlphaGo model performed exceptionally well on Go game, but when it was tried on other games, it wasn't able to transfer its tactics to the other games. Secondly, training time. We see that models created uh, for better accuracy are enormous, and hence the training time is shooting the sky basically. And lastly, that is expensive. We know that the there are companies that can collect data from their users, but not everyone can do that. And data collection takes time, takes effort, and it takes money. So these are the three problems that we face with AI models. And we would basically address these problems through transfer learning. So before we jump onto transfer learning, we need to understand that what is the concept of knowledge transfer. And to understand that deep learning is based on human perception, right? So what would be a better example but human perception uh, to understand this concept? So here's a question that why do most of us prefer a teacher teaching our children instead of them doing self-study? And I am talking about just like your child maybe haven't started going to school. Why, why do you prefer a teacher teaching them? Why don't you just send your child to library and ask them to study on their own? Well, if that was the case, if you sent your a child directly to the library, it wouldn't be a surprise if you ask the child to learn English and the book the child picks is written by William Shakespeare. That's quite probable. And that is why we basically need guidance from an experienced person, because initially there are thousands of paths in front of a child, right? And the teacher basically guides to a specific path, and that guidance helps the child to reach destination. And similarly, when there's a guidance and they know where to go, the learning is much faster, and they do not get distracted by other things. Like if they are learning one thing, so they would just learn that thing. They won't get distracted because the knowledge is vast. So now, what basically transfer learning does? The relationship of student and teacher is exactly transferred from pre-trained AI models to new AI model. So what this new AI model does? Uh, sorry, pre-trained AI model does is it says, okay, if the new model doesn't have enough data to guide itself properly to predict something, then pre-trained AI model provides some knowledge that would help the other model to perform better in its task. But there is an assumption for it for transfer learning. That is that old, which is pre-trained AI model, should and new AI model should be similar to each other in some fundamental aspects. Well, one would ask that why do the AI model need to be similar for transfer learning to work? Well, imagine pursuing a PhD in physics under a supervisor from social sciences, and you would get your answers. So the thing is that unless the knowledge provided by a pre-trained model is relevant to the new model, we don't need the knowledge. Like if a model is for image classification task, we won't expect a pre-trained model from NLP. Like what would be the use of it, right? So this is basically why we need similar models uh, uh, in transfer learning. So now let's see actually how transfer learning happens. And for that, we would be using an example from image processing. So the transfer learning itself is not limited to image processing, but just to understand the concept, we would be using that. So firstly, we have a deep learning model that classifies 10 different types of vehicles. And we trained the model for 10 million 2D images of different vehicles, and it performs very well and give us like excellent results. All is good up till here. Like we are happy that we created that model. We are happy about the results. But now a company contacts us and says that they like our model, and now they want us to create another model, but for 3D images. And that should just predict the images of cars and trucks, but the accuracy of for them should be at least the same as what we are getting earlier. Well, you knowing that supervised learning needs data, realize that they haven't provided you enough data. So you ask the company that the data is not enough. They won't understand because they haven't worked with AI models. So let's suppose they don't understand, and now basically you have nowhere to go. So what would you do? And like how would you get good results because the data is not enough, and that won't help you at all. So there is when transfer learning comes in. It says, okay, if the data is not enough, you don't need to worry. I'll provide you a solution. So what essentially we were using, we would be describing over here, convolution neural network that has convolution layers. So first, to understand the convolution layers, we we can take an example from human eye. Let's suppose I see an image of a door, right? So how my eye works is that the eye actually applies filters to the image. So for first filters uh, decides, okay, these are the edges of the door. The latter filters recognizes the knobs of the door, the pattern on the door, and that's how I recognize a door. And that's exactly how convolution neural network works. The first layer detects the edges of the object. The latter layers detect more complex features of the object. Then comes the dense layers. So does the dense layers do? They simply take the values from the filters of convolution layers, convert it into a vector, and then the weighted sum of the vector results in the outputs. In our network weaver, I'm basically predicting 10 different type of outputs. But now, if we are predicting for 3D images, what we would do? So here we would say that maybe the images are different from each other, but they are still similar to each other in some aspects. Uh, Like I would imagine that the tires of a truck would still be round, and the truck would still have a windows. The truck would still have some similar structure, right? Yeah. Although there would be differences, but I can say that they would be same in some aspects. So what I do is I simply copy all the learned weights from convolution layers to my new model. So all the learned weights from the convolution layer comes right as they are in the new model, and we do not train them. We keep it as they are. And on the latter layers, the dense layers, what we do is that we actually train the model, and we only train the model for the dense layers over here. And after training the model for the dense layers, we just need two outputs, car or trucks. So we would take two output nodes and simply uh, predict the class. It's either a car or a truck, and that's how transfer learning helps us to work with smaller data sets and reducing the parameters that we require for learning. So benefits of transfer learning. First is faster and efficient learning. Let's suppose our model had like 100,000 parameters. And when we applied transfer learning, like we just copied 95,000 parameters as they are and just trained the model for the latter 5,000 parameters. So like we are just now training the model for 5% of the parameters, which would reduce the training time drastically. Second point is better initial model. And that is a very interesting one. Like if we recall logistic regression or linear regression, so we would essentially use zeros vector as an initial condition, initial weights for our gradient descent. But when it comes to neural network, zeros doesn't really work. So like randomly assigning weights were tried, then more researchers came one way to initialize the weights like now for neural network is uh, Xavier initialization, one way is E initialization, Glorok normal initialization, and many more. So, and the basic idea is that the initialization for neural network matters a lot because a slight bit of wrong initialization can lead us to very different answers. And mathematically, we can say that we converge to a different solution. So, hence, better initial model means that when we are using the model, the pre-trained model, to learn and the weights of it, so basically it provides some sort of information that the solution would lie in such ranges. So it would give a better idea for the model to train the weights. Lastly, high accuracy after training. So transfer learning gives us very good accuracy with the results. Like uh, you have less data and it could easily learn from the data and it would give you very good accuracy. But actually, that's not a benefit. uh, it can be seen as a benefit, but actually, if you go into the detail, it can harm your results. So first, and how is that so? So let's suppose uh, we train a model, and a model gives an excellent results with the data. But what our model actually did was it just rote learned the training data. So when we predicted images from it, it failed miserably. So that's in other words called overfitting. And the ways to avoid overfitting, one is simply use regularization. Secondly, uh, it's a good practice that if your data is less, don't train it for a large number of weights. Restrict your weights to minimum so that you can actually learn a generalized solution and not just learn the whole image, rote learn the images basically. So that's one important thing that one should be careful while working with transfer learning. Next is be aware of what you use as your source model, and that's a very fundamental concept that one should be looking at, because if the models are not similar to each other, they would fail miserably. Like if you are again, if I talk about a kid that needs to learn science, and it it goes and you provide it a teacher that only knows like language, some language, like suppose German language. So like there won't be any connection or like any knowledge, any good knowledge that the child would be taking from the teacher, right? And that's exactly what happens in the model, that we need to make sure that a pre-trained model provides some useful knowledge for our new model. Then you should take advantage from pre-trained datasets. And there are many datasets that are trained over time. Like you can find VGG19, ImageNet, MobileNet, and a lot of datasets networks like that on internet. If you're using Python, simply you can load it from Keras and just use it for your transfer learning tasks. They are already trained. So you would just need to train a few days of them and you are good to go. Lastly, and most importantly, larger datasets don't require transfer learning. Once again, transfer learning is only a solution to data problem occurred while using neural networks. It's not an of alternative way of performing tasks uh, for classification and other methods as well. So if we have a larger data set, we don't require transfer learning. And if like I look at in that way, that in the first point I said that if I don't have enough data, so I should use minimal parameters to learn. But if I have enough data, I would be using a large amount of parameters to learn. And if I have the data set as much as my pre-trained model used, I would be requiring all the parameters. I would be training all the parameters basically. So if I would be training all the parameters, what's the use of transfer learning? So now transfer learning has various methods, various implementations. We would discuss some of them. So firstly, using pre-trained CNN features. It's exactly what we talked about earlier. Like we said that lower convolution layers learn low level image features and higher learn complex features. So what to do is like we train the dense layers, or we just like if the problem is a bit different, we change we also learn the complex features again, but we usually keep the lower convolution layers and the low level features of the image same, and we don't change. Now, comes the concept of domain invariant representation. The name sounds a bit weird, and let me tell you that this comes from mathematical topology. And so if you have already lost interest in the slide and you know that you won't understand, just let me tell you that I won't be talking about mathematics over here. So let's take an example from natural language processing. Let's suppose you have a data for tweets, and you train it for sentiment analysis and predict that either it's a positive reaction or a negative reaction. Now that when you combine the data, the vocabulary used in dataset, that would be essentially the input that you will be using. So now that vocabulary basically turns out to be a 5,000 words. So essentially, you would be using a 5,000 dimensional vectors as inputs, right? So you would be using 5,000 dimensional vectors as input. It means like 5,000 words. Now, let's suppose there's an or maybe like you didn't know that what is your test data set, and now when you look at your test data set, it has like 7,000 words vocabulary. So it won't be very wise to use the same network for it, right? Because one has 5,000 words, it means 5,000 dimensional vector, the other has 7,000 dimensional vector. So they don't align, right? So one might think that they are in different dimensions. So here comes the concept of domain invariant. It means that regardless of whatever the dimension of the data is, we just take this significant features from the data and make a collection of them. One way that could be used is like word to vec. If you have heard of it, like if you have used uh, NLP for sentiment analysis, you might have heard of it. It basically summarizes all your vocabulary into a vector of 300 dimension. So now 300 values define all your words in your entire vocabulary, and regardless of the size of your vocabulary, those 300 words vector represents what you have, and that is exactly what is called domain invariant representations. When we are working with domain invariant representation, we often use autoencoders to generate domain invariant data. Now, then comes multitask learning. It's an if you haven't heard of it, uh, uh, I can tell you that I also discussed the same concept in the slides without mentioning what multitask learning is. Let's look at the example when we are taking different vehicles. So what if, let's just consider four vehicles: cars, trucks, bicycle, and trains. What if we have very less images for trains, but we have like sufficient data for cars, trucks, and bicycles? So what multitask learning does is that it provides us a way to tackle the data imbalance. Like if we have lesser data for one class, it's okay. Like if we can predict the other classes at that time perfectly, then it won't harm us. And but multitask learning requires us to have all the data at the time of a training. Like let's suppose we trained a model for dogs and cats. Now we want to introduce a class of parrots with lesser data. We have to train the model again from scratch, and that's called multitask learning. Now, uh, now talking about transfer learning in the context of human perception. So let's imagine there's a child that haven't really seen the world. You you show that child a picture of dog, and later, whenever the child sees, there's a very likely chance that the child would recognize a dog, regardless of the color of the dog, regardless of the breed of the dog. It is very likely that the child would recognize a dog. And it's fascinating, right? Just by seeing one image, and now you can recognize all of the different images. And that's called one-shot learning. Now, again, taking the same example, what if you don't show the image, but you describe the features of a dog to a child, and you say that uh, if you see a dog, it barks like that, it walks like that, and it looks like that, etc., etc., whatever you need for the description, and yet the child recognizes a dog. Well, I mean, if even if the child thinks that uh, there's a possibility that the child can get confused in a cat or a dog, but the voice that you have told that dog barks like that and cat is not like that. So basically, the child could still recognize uh, what is described to them, and that's called zero shot learning. Like without saying anything, you can still recognize what the thing is. And this is one of the hardest problem in machine learning models. However, it comes very naturally to humans. Now, let's talk about the Flynn effect. Uh, Human basically pass their knowledge from generation to generation. As you would know that when we are born, we don't start from Stone Age. Like my parents were born with electricity, and I was born with computers, and a future generation would be born with more technologies over there, and that's how human proceed, and like human basically advance in the world. And basically this is how the technology is also going forward. However, this does not happen in the AI models. However, if we are able to learn an AI model that could learn continuously without forgetting anything, we might be able to resemble continuous growth models followed by humans. That's it for today's session. Thank you very much.
All right, perfect, Wasif. Fatima, if you could please release the form for the survey, or not the survey, the certificate, so people can start filling that out. Wasif, we do have a few questions. Before we get to
Yeah,
them,
sure.
I'm going to steal the
Sure.
screen from you so that I can talk
Okay.
about next week's, or not next week's, tomorrow's webinar, while while I still have everyone here. Let's go screen 2. I think that's the right one. Perfect. So it looks like the certificate, the link to the form there is being shared now. So please, if that's something you would like to receive, fill that out. And I keep trying to say next week, but tomorrow we have Avery Smith, the data scientist at Data Career Jumpstart. We'll have him at noon tomorrow, so the same time as today, for tips for building a data science portfolio. So what Avery's going to be doing is he's going to be going through 5 tips that he recommends to people for overcoming the roadblocks of building a portfolio and making sure that your data science portfolio is top notch. Some things about Avery that I thought about reading out to everyone, but there's so many that I'm just going to look at his his LinkedIn profile and share that. So Avery is he's a data scientist and podcast host at the Data Career Jumpstart. He's a data engineer at MIT. He's a data scientist at Snow Data Science, and he's previously worked as a data scientist at ExxonMobil. So I really can't think of a better person to talk to about data science portfolios. So if that topic is interesting to you, or if you are looking at jumpstarting your career in data science, or just in data in general, I would suggest taking a peek at this tips for building a data science portfolio. All right, perfect. So Wasif, let's answer some questions now. So the first question is from Kessie. What do we do when we encounter data concept drift while using transfer models?
Okay, so again, there are multiple ways. One way to encounter such problems would be to create domain invariant representations that we talked about, and that actually is built to tackle such type of like unstructured changes. But again, we cannot be very certain about it.
Okay. And also I'm going to read a comment, not necessarily a question. Kessie wants to know if we can do a hands-on transfer learning application video sometime. So not going to force you to answer that now, but maybe a conversation we can have after.
Sure,
um, yeah, and Mary is asking, is transfer model helpful for identifying cancer or other diseases?
Actually, transfer learning is very widely used in medical field. Like uh, when recognizing the X-rays and different scans, transfer learning has proven exceptional. So yes, definitely you can choose that.
Okay, perfect. And uh, another question from Kessie, how large of the data size is considered large enough that they doesn't require transfer learning?
Okay, so I mean, there's not a certain amount. Like it's obviously a trial and error, but like let's suppose you are using a network that was trained on maybe like 100,000 images, and you have like for your data set, you have like 90,000 images. So there is not a very large difference in the number of images. And you are using the same network configuration. Network configuration also matters, and the size of the images. But again, there's not a definite number for that.
Okay. That's all the questions we have, but I want to make sure that everyone has a chance to fill out that certificate of attendance form. So we're going to give it another 2 minutes before we end the webinar, just in case anybody else has any other questions. But Wasif, going back to that, we'll call it a tutorial on transfer learning. You know, 1 to 10, 1 being it's not happening, 10 being yeah, let's do it. Or are we doing one,
Sure.
Wasif? Yeah, we're doing one. So Kessie, looks like your wish has been granted. We'll do one. I don't know when. Probably. I know based on our schedule, we're getting booked out through December already. So maybe it's one of our first 2023 webinars. Perfect. Yeah, Kessie, keep your eyes open. This one is for you. All good. So thank you, Asif. Thank you, everyone else for being here today.